All right, so our global systems units. Okay, we started this out and it's pretty short. Okay, only 7 lessons. Right, so there's not a lot to go over, but there's a lot of application in this unit. Okay, and that's what we have to be able to do is apply that small amount of stuff that we learned to the kinds of situations we're going to encounter. So the first thing we covered was climate. Okay, and we talked first about the components of climate. There are 4 components of climate, and that is temperature, precipitation, light, and wind. Right? Those are the components of climate. There was a little bit of confusion about that on a few of the climatogram activities that I marked. Okay? In the hypotheses, a lot of people said if the factors affecting climate are temperature, precipitation, light, and wind, well, that's wrong. Those are the components of climate. The factors affect those things, like being close to the ocean affects your temperature and your precipitation. Being in a mountain, in a rain shadow of a mountain, affects your precipitation, and so on. So there's some confusion on that. Make sure you understand the difference. The components are these 4 things. The factors are the things that can change those. Okay, speaking of factors that affect climate, okay, we talked about these ones here. Okay, latitude, altitude. Okay, both of those have pretty major effects on your temperature. All right, mountain barriers, which can affect your precipitation if you're in the rain shadow, or if you're on the windward side, it can affect you having more precipitation. Proximity to oceans, that can regulate your temperature and in some cases make it wetter. Okay, centers of high and low pressure, okay, prevailing wind patterns, all that kind of stuff. Those are all factors, okay, that affect climate. Just where they typically come from. And again, that's kind of a latitude thing as well, but yeah. Right. We're in an area that fluctuates. We're kind of like up in like the Northwest Territories, none of it is typically a high pressure area. Over like Prince George, like, you know, kind of northern BC, there's a big low pressure area that typically sits there as well. So if you're in one of those areas, like Prince George was the wettest city you had on the climatogram activity, right? Whereas Iqaluit was very dry. Right, so things like that, right? But we're in an area, again, if you don't like the weather, wait 5 minutes, right? Like it's always changing here. All right, so how is this going to get tested tomorrow? Okay, well, the answer is this. I'm going to give you a picture of a map of Canada, and I'm going to identify a city on that map. Okay, so it'll be on there in case you don't know where that city is. If you don't, you should really review your Canadian geography. But, okay, I will show you where it is on the map. What you will be asked to do is describe what you think the climate of that area is like and why. Okay, the why part is going to need to include those factors. So basically what you did on the climatogram activity, except this time you have to come up with it on your own. Okay, so you'd say, well, that city is, you know, close to a mountain barrier, so it would likely be in the rain shadow and would get less precipitation. So you're talking about here's a factor, here's how it would affect the component, okay? Or it's got a very high latitude, here's how that would affect it. It would be cold, okay? Things like that. Everyone kind of follow? Right, so you're integrating both of those things. I'm identifying, based on this location, here are the factors I think would affect that city, and here's how they would affect it: temperature, precipitation, light, wind. No, just the ones you think are important. Probably like the top 3 or 4. Okay. Same question. Okay. All right. That makes sense. That's how you're going to have to apply what you know there. So you have to know all of them, and then you have to be able to apply them. Okay. Explain how the factors make the climate, which is the components, the way it is. Yeah. Nope. But I mean, I'm going to pick one where things are going to be fairly obvious. Okay. Like it's either something you're going to be so familiar with that you would know that, or its location would make those kinds of things obvious. Yeah. All right, so that's the first thing we went over. Okay, then we talked about climatograms, and yesterday we said you're going to have to match the climatogram with a biome and explain 5-mark question. Okay, so you'll get the climatogram, 2 marks will be explaining what's on the climatogram. Okay, so you look at the climatogram and all the precipitation bars are very level all the way across. Okay, and they're very high. Okay, like they're over 200 millimeters, and the temperature line is flat. Okay, so you would say in your description there then, this climate is, or this location is clearly equatorial because the temperature doesn't change. There's no distinct seasons. There's also a high amount of rainfall, 2 marks. Okay, you interpreted the climatogram. Then you'd identify what biome you think that comes from. Tropical rainforest, 3rd mark, right? And then another 2 marks for explaining why. Okay, well, the tropical rainforest is like this, and so on and so on. Okay. Questions on the climatograms. That's all you're going to have to do with them. Okay, there'll be a climatogram. You got to tell me what biome it comes from. All right, energy transfers in global systems. This one is involved in several questions, and they're all application. Okay, so this was that day where we went over the 3 fates of sunlight. Okay, when light strikes the Earth's surface, 3 things can happen to it. One of them's already up there. Absorbed, reflected, or used. And when it's used, it's what process? Photosynthesis. Should I hear anything about solar panels in this question? Okay, please don't. All right. Whether it is absorbed or reflected is based on this thing, albedo. Okay, remember that albedo is the reflectivity of the surface. High albedo is highly reflective. Low albedo is very absorbing. Okay, so we need to remember terms like that. Okay, so there'll be something there like, you know, here's a location. Tell me what happens to the sunlight. Okay, you just basically have to explain. No, albinism is a genetic disorder. It's named something. It's named differently because it's not E, it's I. Albinism, right? Yeah, they're all like 4 or 5. Well, you identify the 3 things and then explain. Yeah, but tell me what happens. Like when it's absorbed, okay, what happens to the energy of that area? It goes up. Okay, when it's reflected, nothing happens. When it's used, it's converted into chemical energy by, yeah. Okay, it's a mark for identifying the 3 things and a mark for your explanation. Okay, given that area. Okay, if I said it hits a tropical rainforest, which one of these is bigger, absorbed, used, or reflected? Used, yeah, it's all plants, right? So it's going to be situational. Okay, you have to kind of adapt your answers. These 3 things are happening, but which one's bigger? Right? In reference to where it's hitting. It's hard to say how it's measured. Basically, you would measure albedo by the change in energy of that area when sun encounters it. Yeah. Okay. Like right now, the change in energy isn't very much, right? Because it's all white. Okay. So we talked about those things, and then we also talked about the atmosphere, the hydrosphere, and the lithosphere. Okay, and the different roles that they play. Which one's the most important in terms of transferring energy? Okay, the atmosphere. So if we're talking about global energy transfers, we're talking about the atmosphere because the lithosphere basically has no role to play in that, okay, other than it provides soil for plants, which is not really, I mean, it's not that that's not important, but it's not transferring energy from the equator to the poles. The other thing we need to watch for is what are the mechanisms, okay? So within the atmosphere, how does energy move? Okay, Okay, and a Hadley cell is an example of a convection current. Okay, so either one of those terms is good, but okay, make sure you're describing that the air moves because of changes in energy. All right. What else can move from the equator more north that carries energy? Okay, the jet stream, yeah, is a different wind pattern. Wasn't what I was thinking of, but it is one of the 3 things. Okay, wind is the convection. I'm thinking something that stores a lot of energy, happens at the equator, but moves away. Clouds. What's in the clouds? 2 words. We did problems to do with it. Latent heat, okay? Latent heat, guys. Latent heat is huge, okay? Remember how much energy is stored in even 1 gram of water vapor. Okay? If you have a large moist air mass move from the equator northward, it is carrying like unimaginable amounts of joules of energy in it because of all that latent heat. So you got convection, you got latent heat, you got the jet stream. Okay, those are the big three in terms of the atmosphere being able to transfer energy from the equator to more northerly parts of the world. All right, there's definitely going to be some questions asking you about the mechanics of that. I will, I'll get to it. Okay, that has to do with prevailing winds. Convection currents is hot air rises, cool air descends. Okay, so guys, with a convection current, okay, like how many of you have ever been to the ocean? Okay, felt a sea breeze before? Okay, a sea breeze happens kind of late morning, right? So if those are waves, that's the ocean. I can't draw, you guys know that already. Okay, and here's the land. There's a tree, just so we can tell them apart. Okay, when the sun shines on this area, the land heats up faster than the water does because water's got a high heat capacity and a lower albedo than the land does. Okay, higher albedo than the land does. So what happens is the air above the land heats up faster and rises. As a result, cool air blows in off the ocean to replace it. This air can't fall back down now, okay? It's already risen. I'm going to use red here, okay? It's already risen and air has moved in to replace it. So it starts to move this way and you get a convection current, which is like a Hadley cell, okay? That is going like this, okay? That's just how energy moves in a fluid through a convection current. When we talked about that diagram with prevailing winds, right? And we had the different convection currents, the equator gets more energy, right? The equator gets more energy than anywhere else, right? So there's more hot air there. When it rises, air from the north moves down to replace it. So that hot air now is forced to go northward above the cooler air that replaced it. That's how it starts that movement. Okay, then it encounters another Hadley cell at the higher latitude. Okay, that starts that other process. Okay, where the wind can turn the other direction instead of coming from the northeast. Okay, we'll go over it again. Right? Basically, it's more a mechanical thing that you need to just memorize as opposed to apply. Okay, that prevailing wind part anyway. All right, so within the atmosphere, it's the most fluid, so it has the most or the largest role to play in energy transfer. Okay, so we got wind, which is convection. Okay, we got latent heat, and we have also the jet stream, which for some reason isn't listed there. Okay, those are the major energy transfer mechanisms within the atmosphere. Okay, and you can see I've drawn this little like grappling hook type shape here. Okay, this is to show you that the atmosphere and the hydrosphere interact to produce the latent heat. Okay, without the hydrosphere, there'd be no source of water to be evaporated. So that's kind of a place where those two parts of the Earth interact. Okay, the water is evaporated from the hydrosphere and put into the atmosphere. Okay, the hydrosphere also does some convection. We have ocean currents, okay, that happen as a result of convection. You got different, El Nino and the North Atlantic current and all those kind of things that can go on. But again, not as big a deal as the atmosphere. The atmosphere is everywhere, touches all parts of the Earth, so it's more important in terms of transfer of energy. Right, and then we also had the lithosphere, which basically is just absorption. Okay, it absorbs the heat energy, okay, reflects some of the heat energy, and provides a substrate in which plants can grow. Okay, and within this, we've now mentioned convection, and we've got conduction written here. Conduction, remember, is how, heat energy is transferred through solids. Okay, requires the particles to be in contact with each other for it to work. Okay, so the particles have to be able to physically run into one another for conduction to transfer energy. The third method of energy transfer, we got conduction, we got convection, we got radiation. Okay, and when we talk about these three things, these all have to do with radiation: absorption, reflection, being used. The thing that's being used is radiation. Okay, light is a form of radiation. All right, so you'll be asked about those in terms of an application question as well. Okay, I think this was a drawing of fiberglass insulation or something like that, because like the wall, I drew it before. Okay, so what you're going to be asked to do in terms of an application of convection, conduction, and radiation is exactly like the question that's on your review sheet about designing a building that could keep food cold in California. I think it was, what number was it, 10? 12? Okay, so what we're looking at there is, how can I, in this situation, either use to my benefit or thwart these heat transfer processes? If I'm talking about keeping foods frozen in California, I am trying to stop the absorption and transfer of heat energy from outside the building to inside the building. All right, so the first thing I want to stop is the absorption of radiation. Okay, I don't want heat to get in by radiation, so the best way to keep radiation out is to do what with it? Make it highly reflective, right? Make the surface high albedo, okay? Make it white, okay, or something like that. A lot of people say I'd cover it in like shiny metal. Shiny metal is, yes, shiny and has a lot of glare, but it actually absorbs a lot of energy, okay? It looks like it reflects, but it actually absorbs quite a bit, and metals transfer energy easily, okay? They're very good conductors of heat, so generally that's not a good process. If you could make it out of something that's not going to transfer heat very well, like concrete or something, or fiberglass, okay, and then make it a light color, that would be a better way to approach that problem. Now you're reflecting the energy away. Something, as long as it's white. Basically, you need to show me, I understand, Mr. Coder, that the way to stop radiation from getting in is to reflect it away. Yeah, or draw the building, right, that you were going to do, and yeah, and label the parts, but then also explain. Like if you just draw a diagram, I'm going to go, nice picture. Okay, but I can't follow your thought process from the picture. I know, and no, a picture is not worth 1,000 words. Okay, yeah, because like I actually had a kid tell me that when he got 1 out of 5 for only drawing a picture. He's like, but Mr. Cudero, look at the picture. I'm like, it's a nice picture, but you didn't explain anything. It's a picture of a building. I don't know what this is. Like, you know what that material is, but I don't, because you didn't tell me. Okay, and you didn't tell me why you used that material. You have to explain that to me. Okay, so if you draw the building, then you say, well, my building is white, and that reflects the radiation away, which would keep energy from being absorbed. Okay, and then you say, well, I would put in the walls of my building fiberglass insulation, or I'd make them a vacuum so that no energy could move by convection from the inside or from the outside to the inside. Okay. No, you can make it as long as you have a double layer, right? You could make it a vacuum. You just got to make it a strong enough material. This has got a vacuum in the middle. It's not collapsing. Right? I'm not saying it's easy. Like you can't make it out of something flexible, because you're right, the edges will suck together, right? So yeah, talk about how you would use that or prevent it, and then same thing with conduction. Right? You got to insulate against conduction by trying not to have too many contact points between the outside and the inside. The more contact points, the more conduction can happen. So all of those things, just applying what you know to that situation. Does everyone understand there? Okay. All right. Okay, wind patterns. Right, so talking about prevailing winds. Okay, the jet stream's got a bit of a role to play in there, but it's also a big part of that other thing. Okay, so the jet stream is a wind pattern as well, and its position is dictated by centers of high and low pressure. Convection and the Coriolis effect are what cause the prevailing wind. So this goes to that diagram you were asking about. Okay. Oh, there's a terrible drawing of it. You know what? I'm just going to pull the picture up again. All right, so when we're looking at this diagram here, again, the equator gets the most solar energy. Okay, so when solar energy strikes there, the hot air is going to rise. Okay, now because the air that's moving in to replace it is coming from still like not a really polar area, that air is reasonably warm as well. Okay, so this air is moving in to replace it, and as it moves downwards because of the convection current and filling the void that's produced by the rising air, okay, the Earth spins underneath it. So even though this air is only moving from north to south, we're being moved through it while it does that. So that makes it appear as though the wind is doing this, even though the air is really just trying to move from north to south. All right. The air above now can't come back down, so it's forced to move northwards. Because it's at a high altitude, it cools off a little bit, okay, as it comes to here. And then it can actually kind of go both ways, but it tends to generally wedge under. Okay. Now, comparatively, it's warmer than this high latitude, high altitude air. So it'll wedge under as kind of warm air. And as it tries to move this way, again, we move and rotate underneath it, which tends to deflect it and give us these westerly winds that we typically experience here. Okay. Near the pole, you have the same thing happening as is happening at the equator. Okay. Cold air is rotating around and it's moving southward. And as it moves southward, we rotate into it, so we get a polar easterly. Okay. So this happens because of the interaction of convection and the Coriolis effect. Yeah, a Hadley cell is a type of convection current. Okay. So if you're being asked to explain how prevailing winds happen, those are the two mechanisms that produce the effect we recognize as prevailing wind. Okay? The fact that there's unequal distribution of solar energy, the atmosphere is trying to balance that, so it's moving because of, and that's convection, and the Earth rotates while that's happening. Okay. Yeah. All right. Okay, and obviously jet streams, they play a big role as well, especially as an energy transfer mechanism. They kind of, do this serpentine thing, okay, all along the northern hemisphere, okay, and that produces obviously changes in the weather as those go along. All right, for number 5, okay, specific heat capacity. You're going to have one specific heat capacity problem in the written response section of this exam. No, not water. Okay, that's a latent heat problem. Okay, this is just going to be a specific heat problem. So like, let's say you go outside and you put like, I don't know, a wrench on the driveway in the sun. Okay, after a while, the wrench has absorbed 500 joules of energy. Okay, the wrench is made of steel. What's its final temperature or something like that? So just a single, it's not water, it's another material. You just have to do an E equals MC delta T calculation to solve the problem. Yeah, well, I tell you, it's made out of steel, and then there would be a chart with the numbers on it, or I would just give you the C in the question, one way or the other. All right, so you will have one of those, specific heat capacity problem. Okay, why do I have proximity to oceans down here? Oh, right. Sorry, that relates to proximity to oceans. Remember that the ocean is made of water, in case you didn't know that. Okay, and water has a very, very high specific heat capacity. So that is why being near the ocean can regulate your temperature and affect your climate. Okay, as a factor affecting climate. Okay, it has a high heat capacity, so it can absorb a lot of energy or lose a lot of energy, but not change temperature very much. Okay, and that helps to regulate the temperature of the nearby areas. Okay, and then we have latent heat problems. Okay, so a heating curve problem. You're going to have one of those. Okay, they all work the same. You got to draw the heating curve, identify start and end, figure out how many steps, solve the steps, add them up. Do you need to memorize what, sorry? Yes. Anywhere the line's going up, that's that kinetic thermal energy, right? If it's going up, temperature is changing. You can only use a formula that has that. Where it's flat, you can't use it because there's no temperature change. So you have to remember that when it's freezing, use MLF, okay, or melting, okay. When it's vaporizing, LV. Yeah. Okay, because I will give you those formulas on the test, but I will not give you this picture. And you have to remember that water melts at, or water freezes at 0 and boils at 100. No, that'll be on the test. Because it has to do with the movement of the particles, right? Kinetic is movement. So how fast are the particles moving? Potential thermal energy, how far apart are the particles, right? Because they can move back together. They have the potential to move back together. Okay, and then last thing we went over, biomes. All right, we already talked about how one of those biome questions is going to be with the climatogram. There's a number of multiple choice questions that contain a picture and a description of a biome. You have to match them up. All right, let me give you some numbers here. Okay, so you have, oh, don't forget about the water cycle as well, guys. Yeah, because we talked about that briefly as well. There's 25 multiple choice questions. So it's actually the least number of multiple choice questions of any test you've had, because I think physics had 27. Okay, so there's 25 multiple choice questions, but they're quick. Okay, like you'll get through them very, very quickly. And then there are 9 written. Okay, and we've basically talked about all of them already. Okay, and we've talked about the climatogram, we've talked about the place in Canada, we've talked about wind patterns, Coriolis effect, the 3 fates of light energy, application of heat transfer principle, so convection, conduction, radiation, specific heat capacity, latent heat, and one question that kind of works all of that together at the end. Okay. Questions on what's on there? Oh, here I said I was going to give you numbers, and then I didn't give you that one. So it's we've got 71. So there's 46 marks in the multiple choice. Okay, figure that's 9 questions. They're all on average around 5 marks. Okay. Any other questions there? All right. If you haven't done that review sheet already, that would be a good idea. No, because there'd be no way to prove that we were at fault for it. We would all come though. We would all be there.